All right. First of two sets of tutorials on analysis of variance. This first one introduces what's called the one-factor ANOVA, and then we'll move on to the two-factor or factorial ANOVA. ANOVA is one of the biggest set of procedures within psychology. It's really the go-to when you have experimental type data. Very, very widely used, so much so that our department offers an entire 400 and 500 level course called Analysis of Variance, which is a very common thing for most schools to have. All right, what is analysis of variance? Well, the abbreviation is ANOVA for analysis of variance, just comes from the name there. ANOVA actually refers to not one single procedure, but it's really many procedures. And what we're talking about are procedures that, like the t-test, compare means. There's the one factor between subjects ANOVA, which is the topic of this tutorial. There's also the one factor within subjects ANOVA. I think the analogy here is the between subjects ANOVA is like a t-test. The within subjects ANOVA is like, the between subjects ANOVA is like the independent samples t-test, whereas the within subjects ANOVA is like the paired t-test. There's the factorial ANOVA. That would mean an ANOVA with more than two factors. You could have a between subjects and a within subjects version of that. You could have a mixed model ANOVA that has at least one between and one within factor. You could have ANCOVA, MANOVA, multivariate analysis of variance. ANCOVA is analysis of covariance. MANCOVA, multivariate analysis of covariance. So lots and lots and lots of different procedures fall under the ANOVA arm. ANOVA is primarily attributed to Sir Ronald Fisher, another old person we're talking about. He discovered what's called the F distribution, which is used in ANOVA and certainly many other applications. Credited with numerous statistical innovations. And one thing, he and Pearson absolutely hated each other. They could not stand each other. They were constantly criticizing each other's work. Really, really nasty. In fact, the only thing that they could agree on was being straight up racists. Yep. Another old white statistician who was a horrible racist who believed that the best way to have quality human beings was selective breeding, where you didn't let people of color have children. So I am probably sensing a trend here. Again, keep in mind, Fisher may have been a horrible person, but his work is completely separate. I mean, the work is mathematical. It doesn't have a perspective on race. All right, one factor between subjects ANOVA. Let's unpack what that term factor means. Factor would also be known as independent variable or grouping variable. One factor designs compares means across two or more groups. Now, if you remember the independent samples t-test, that compared means across only two groups. One factor ANOVA can do two groups, but it could also do three groups, four groups, five groups, however many groups. For example, we might be interested in the effectiveness of a variety of different types of bulimia treatment. We could have a control group where people got no therapy, a cognitive behavioral therapy group. We could add in a psychodynamic group. T-test wouldn't be able to handle that, but analysis of variance can. The groups within the factor are called the levels of the factor. So you have the factor, and then the different groups are called the levels. You have to have at least two levels, otherwise you don't actually have a factor. All right, one factor between subjects. What does between subjects mean? Between subjects means we have different people in each group. So different people in each group. This would be analogous to the independent samples T, but again, the big difference is ANOVA can handle three or more groups. Similarly, we have within subjects ANOVA approaches. That's analogous to the paired t-test, where we have the same people in the same groups, but now it's three or more. We can handle three or more, not just two group situation. And then finally, the term ANOVA. ANOVA focuses on variances. And broadly, when we say variances, the core piece there are what we call sums of square statistics. It may sound like I'm repeating myself because this is what we talked about with regression. ANOVA and regression, as we'll see, both focus on sums of squares. We're going to start with a total sums of squares. Again, I'm repeating myself because that's what we do with regression. And then when we break it into what we can explain and what we can't explain, again, just like regression. What we can explain is called between group variance in this concept. It's what's explained by being in one group or another. Why one group had, how different the means are from one group to another is one way we can think of part of this. Within group variance is what we cannot explain. How much scores move around the mean of their group, how much the variability in scores is something we can't get at. This is these two pieces. The sums of square between is analogous to sums of square regression. Sums of square within is analogous to sums of square residual. We'll talk about that in a little more fine detail at the end of these slides. The formulas that we have here, they again have that familiar sums of square format. The different notation here, x bar sub t is commonly called the grand mean. It's the mean of all of the scores. We've dealt with that concept before. There's just a slightly different notation here. Keep in mind, the notations are going to differ between regression and ANOVA because Fisher and Pearson hated each other and really wouldn't acknowledge each other's work. And we'll see there's some ironies in that as we get to the end. X is the individual score. Again, we saw that before when we were doing regression. It was simply called the Y score. X bar sub J, that's going to represent the mean of the group that the person is in. So each of the groups that we have are going to have a mean. X bar sub J represents the mean of those groups. You can see the sums of square total, difference between the individual score and the overall mean. Again, something that should sound familiar because we've seen that concept before. Between group, we've got this n sub j there. That's the number of people. That's the number of people in each of the groups. That gets multiplied by the mean of the group, multiplied by minus the overall mean. We'll see that that is just a shortcut. That's helpful to ease calculations. We can do this in a way similar to regression as well. And then sums of square within, how much the individual score differs from the mean of the group.
Oh, we're done. It went very bad. It's clean.
Quiet.
Okay.
Giving a lecture here. Come on. Sorry. And as we saw before, the sums of square total gets broken into sums of square between and sums of square within. So what do we do with these sums of square values? We're going to end up ultimately calculating a value called f. Because of course, Fisher named the endpoint statistic f after himself. At least Pearson didn't do that. F, like T and Z, reflect scores on a distribution that tell us how likely our sample results would be if the null hypothesis was in fact true. Again, same exact concept for every hypothesis testing thing we do. There's a real consistency here. We just have different procedures that have different statistics because they're different research situations. F is constructed by dividing something called MS, the mean square, for between group over the mean square within. We haven't seen mean square statistics, but we'll see that they're very easily calculated once we have the sums of square statistics. So don't let those frighten you. Right, the mean square value, it's just a sums of square value over a corresponding degrees of freedom. With ANOVA, we end up having two types of degrees of freedom between group and degrees of freedom within group. We didn't have to have this with the t-test because every time we do a t-test, we have exactly the same number of groups. ANOVA, that varies, and we have to take that into account. So the mean square between group, sums of square between over degrees of freedom between. Mean square within, you could probably guess this at this point, sums of square within over degrees of freedom within. Degrees of freedom within is defined as j minus 1, where j just simply means how many groups do you have. So if we had 3 groups, j minus 1 would be 2. Degrees of freedom within n minus j, number of people minus the number of groups that we have. With the t-test, this was number of people minus 2. Why 2? Well, 2 is the number of groups you have. It's the same concept. We just have something that varies now because we can have 2 or more groups. So what do we do with that F value once we get it? That's going to allow us to test our null hypothesis. The null hypothesis is always that all groups have equal means. So we can't say mu1 minus mu2 minus mu3 equals 0, because if they were all equal, that wouldn't actually equal 0. Let's say they were all 5. It'd be 5 minus 5 minus 5. Well, that'd actually be negative 5. So we just have this simpler conceptualization. All of these values are equal. Like with T and Z, we can compare our F value to a value from a table. We probably won't do that. I'll probably show you a little bit with that. But we're not really going to do that because the more standard way would just be to get R to give us a value. This is what an F table looks like. What this is doing is it's giving cutoff values for F at 0.05. And one thing to note here is that it uses 2 different degrees of freedom. So we might see the terminology somewhere: degrees of freedom numerator, degrees of freedom denominator. Numerator means what's in the numerator of the t-test. Well, the between group is in the numerator. So that's going to be the degrees of freedom between group. Within is in the denominator, so it's going to be degrees of freedom within for the denominator. You simply line up the different values and pluck out the comparison value. That's the old-fashioned way to do it. One thing to note here is all of these values are positive. We don't have a 2-sided distribution like we did before. The reason is that we're working with values that have been squared, so everything's going to be positive. Also, like with T, we have a value called a measure of effect size. In this case, we express the effect size with the 1-factor ANOVA using a statistic called eta squared, which is the sums of square between group over sums of square total, or the sums of square for what we can explain over the sums of square total. One thing to note there is that's just like R squared. In fact, that is the same as R squared. Again, why is it different notation? Well, again, Fisher, Pearson. They don't communicate with each other, or when they do communicate with each other, they're calling each other names. So they don't recognize each other's work. And again, the irony being here, they both landed on the same spot.